But the thing about building a periodic table from math, I mean, math can give us an idea of what those abundances should be. The simple mathematical relation that as z gets bigger, as atomic number gets bigger, you have less of the thing. That's actually a statement that's also reflected in the periodic table. As it gets bigger, you get lower on the periodic table. So the question is, you all know, you probably heard of Dmitri Mendeleev. And he was the first one who really put it all together and said, there is a table to the elements. There is a repeating pattern, and it goes by this pattern of 2, 6, 10, 14, you know, before they figured out that that had a quantum mechanical reason for it that we talked about in the previous lecture. So Mendeleev did that by looking at the data and sliding around cards on a table until he realized that there was a way to arrange the cards that had a deep repeating pattern. And he used that to predict some things. Now, the story is really a lot more complicated than that, but the basic idea is he was working from the data, and he saw a pattern in the data. If he was working with the data's numbers. Computers are really good at working with numbers. Is it possible that a computer could recreate the table not knowing anything but the numbers, the type of numbers that Mendeleev used? So we'll use something called principal component analysis to analyze that. I just want to ask you, have you had Dr. Pierce? Does she ever talk about PCA in any of her classes?
I feel like I've heard that before.
She probably mentioned it, but right. That's how people usually refer to it as. So principal component analysis is what Dr. Pierce does her research on. And so she gave me these slides, so I've got to give her credit for this. But I want to explain what it is because it is a method that the computer can use to recreate the periodic table without knowing anything other than, I want you to put these elements into a pattern. Can you find a pattern in the way these elements work? PCA finds patterns in really complex data. So this is her tutorial for how it works. If you have a bunch of samples, and let's say you have a property for each of those samples, variable 1 and variable 2. And you see right here we have a range of properties. Variable 1 goes from -10 to +10. Variable 2 goes from -8 to +8. Is there a pattern in that can we group the samples together into just a few groups so we can say group A, group B, things like that? Well, looking at it like here, you don't really have much hope of doing that by yourself. The computer, however, can look for groups and it can find statistical patterns better than we can. It uses PCA. So the simple way to do PCA is if you have two variables, you do an XY plot of each of your samples according to the two variables that they have. And for our example of elements, it would be like variable 1 might be molecular weight, variable 2 might be ionization energy or something like that, something that you can easily measure, put a number to. But for just any group of variables, if you do this, and if you plot all these out, well, if you look at this, you can already see that there is some kind of pattern, right? As variable 1 gets bigger, variable 2 tends to get bigger. And as variable 2 gets smaller, variable 1 tends to get smaller. It's not a one-to-one relationship, but you can definitely see that that relationship can be represented by a line. So we can take the data and we can do a line fit to it. And if we can say the data looks like it lines up in this way, we call that our principal component. The line that the data lines up on is our principal component. We call it principal component 1. The thing is, if you look at it, you can actually see that there might be another line. And this is the inside of principal component analysis. What if there's another line at right angles that could fit the data? That would be principal component 2. This affects the data much less, but maybe there's some kind of correlation in another direction that would reveal something about the way the data should be grouped. Okay? So they called that line principal component 2, and Dr. Pierce knows all about how you actually set the lines. I just know that you define them this way. And you give it a score, like principal component, how far it is along this line is its score for principal component 1. How far it is on the PC2 line is its score for principal component 2. And then you can do things like loadings. The angle of the line with the axis is called the loading, or actually the cosine of that angle. All this is a lot of math, and actually Dr. Pierce is being called, excuse me, Dr. Pierce is being called to go and present on how she does this for samples. So these are some data, and basically you can do this with a large data set, thousands of variables, and you can discard the smaller principal components. Like the PC1 is a big principal component, PC2 is a smaller one, and sometimes they get so small that you just discard them. Those will help you to actually group the data into different groups. So what you do is you take the scores on PC1 and PC2 according to that. You don't have to replicate this, by the way. I just want to show you. The math itself is actually pretty simple, but you're dealing with large data sets, so that's why you give it to the computer to worry about. You basically make your data, you plot your data as if PC1 and PC2 were your axes. And you do a plot of loadings as well. So remember, the loadings are the angles. And the way that Dr. Pierce actually does this is this is called chemometrics, because you're applying a measuring sort of process to chemistry. And so let's say that she took gasoline, 210 gasoline samples, and she wanted to see are the samples chemically different. Now the only thing that she knows about them is she ran them through a column, so they had retention time, and you have a signal off the column. You don't know what this signal is. You just know that you run this one gasoline sample through and you get this pattern of peaks that come off the column. It's like a fingerprint. And you run all 210 samples through and you end up with 210 different spectra, tons of data, each with hundreds of data points. But the thing is, so what Dr. Pierce wanted to know is the gasoline that I get from one gas station versus another gas station, is it chemically different from the other ones? Well, if you look at this, you can look at them by eye and you can see there might be some kind of differences, but you want to prove whether there are some differences. And so what she did is she did a principal component analysis and took those 210 gasoline samples and she labeled the source of each sample with a single letter. She got one from a Chevron station, one from a bunch from a Chevron station, a bunch from a Mobile station, Tesoro, Shell, and Arco. And the computer, without knowing anything about them, just took the numbers that it got from the analysis. It took the chromatograms that it got. And it said, these chromatograms are similar to each other. These chromatograms are similar to each other. And so you can see from this which samples are similar to which other samples. And apparently there's something in the chemistry. I mean, Chevron has like the Techron stuff that they put in. And that shows up as a peak on the graph probably. And the computer sees that and puts those together. Principal component analysis is like taking these and just saying that I see a lot of chemical similarities between all the Chevron samples. But it's really cool once you do this because you can say things like Chevron gas is pretty close to Mobile gas. It's definitely closer to Mobile gas than Shell gas is to the other two. And what is the weirdest outlier of all five of them? If you wanted to say what's the most unusual gasoline of the 5 stations, yeah, you've got Arco, right?
Is that one I heard of? There's an Arco and there's a Shell
Uh-huh.
right next to each other in my town, and that's why everyone always says, like, your gas and Shell is
Right.
something.
Arcos is 2 different, Dr. Pierce says she thinks it's something having to do with the ethanol that they add because they definitely do add more ethanol or maybe a different grade of ethanol to make it cheaper. Because Arco's thing is to go for price, not performance. And it's very clearly stands out. And this plots with prices, you already know from going around. So here we have a computer. The computer didn't know the prices. It didn't know which station it came from. But it put them together, and because it's an objective grouping, you can draw some weak conclusions from the fact if you have something distant from something else, it's probably chemically different. Something close is probably chemically similar. This is exactly what Mendeleev did with the periodic table. So that's what the paper is, and I'm going to show you that these papers exist. I'm not going to make you read them. But I'm going to say that these papers exist because they really connect PChem out to these different concepts. This is a paper where they took the PCA and they took the data from the elements. This is the data that they took, atomic number of course, and they took the atomic weight, radius, the ionization potential, the EA, electron affinity, and electronegativity. So they took those different numbers. And again, you can look at those numbers all you want, and maybe you can see some trends, but you can't really group them that closely. PCA lets it put those down, slides them around, and it puts ones that are similar next to each other. And remember that it's going not just from atomic weight, but it's going from a lot of other things as well, things like ionization potential and electron affinity. They don't go up with size. You can have a very large, I mean, they have a weak relationship with size, but there are other things like the electron orbitals that matter a lot more. So it took those numbers from the textbook, did PCA analysis, and this is what came out. It found that there were two principal component axes, so you can put it on a nice two-dimensional graph. And if you look at that at first you're like, okay, well that looks like a mess. But if you look at it a little bit closer, I have colored it, in this case, the same way that this periodic table is colored. So let's start with the, actually we don't have data for the noble gases because I think that they're just way off the chart in this case. But we do have data for light blue, which is the halogens. And look, it puts all the halogens together, and it puts the fluorine at top and the iodine at bottom. And if you look over, okay, well here's nitrogen, carbon, oxygen, and then you go down, you get sulfur and selenium. That matches this sort of gray area. The light green area, that sort of matches. And remember that these axes, they're just measures of similarity. So we shouldn't expect it to come out with a straightforward grid. We just want it to have the arrangements. We want stuff that's close to be close to each other. And we want to see the same arrangement of atoms. And if you look at it color by color, you can see that it totally recreated the periodic table from just the data that we were given, those 4 or 5 data points for each one. Do you have a question? Yeah. Yeah. Yeah, so atomic weight was clearly probably one of these principal component, probably this principal component axis, the y-axis, is closely related to atomic weight because you see down at the bottom you have all the big things and up at the top you have all the light things. But it also combines it with the other things because it's able to combine all the variables and to find the variation. What are the axes of variation? So that's basically what I know about principal component analysis. Again, Dr. Pierce is a world expert in it. But that's one of the main points about it. Now I want to break these up into shorter things. Also, I want to make